5.2, verifying trigonometric identities. Okay, so this is where I can't tell you what to do. There's many ways to do it. This 5.2 is a worksheet, so there's multiple ways that you can do your worksheet. If you come ask for help, I might show you a different way that you never thought of, or you might show me a way I've never thought of. So with 5.2, it's just do the best you can. You have to really think outside the box here. So hints for verifying identities. So remember, verifying means make sure it's true, make sure it's equal. Learn the fundamental identities. Whenever you see either side, that's supposed to say side, of a fundamental identity, the other side should come to mind. Also, be aware of equivalent forms of the fundamental identities. For example, sine squared theta equals 1 minus cosine squared theta is an alternate form of sine squared theta plus cosine squared theta equals 1. Remember, we've talked about that. Equivalent forms. 2. Try to rewrite the more complicated side of the equation so that it's identical to the simpler side. 3. It is sometimes helpful to express all trigonometric functions and their equations in terms of sine and cosine and then simplify the result. So meaning, if you're stuck, try sine and cosine and see if that helps. Usually any factoring or indicated algebraic expressions or operations should be performed. These algebraic identities are often used in verifying trigonometric identities, so meaning if you can factor, you have to factor. If you can factor cubes, factor difference of squares, you have to do it. You have to factor. So having this part just in your back pocket, really, really useful. The sum or difference of two trigonometric expressions can be found in the same way as any other rational expression. So say you want to add 1 over sine plus 1 over cosine, you find the LCD and add them. That's all. So you treat this as everything we've always done. 5. When selecting substitutions, keep in mind the side that is not changing, because it represents the goal. For example, to verify that the equation tan squared x plus 1 equals 1 cosine squared x is an identity, think of an identity that relates to tan x to cosine x. In this case, because secant x equals 1 over cosine and secant squared x equals tangent squared x plus 1, the secant function is the best link between the two sides. So meaning, I need to use math to prove tan squared x plus 1 equals 1 over cosine squared x plus 1. We do that by finding common ground. 6. If an expression contains 1 plus sine x, multiplying both numerator and denominator by 1 minus sine x would give 1 minus sine squared x, which could be replaced with cosine squared x. Similar procedure apply for 1 minus sine x, 1 plus cosine x, and 1 minus cosine x. So, verifying identities by working with one side. To avoid the temptation to use algebraic properties of equations to verify identities, one strategy is to work with only one side and rewrite it to match the other side. So we have to verify this identity. We want to verify that cotangent theta plus 1 equals 1 cosecant theta times cosine theta plus sine theta. So you always want to work with the harder side. Work with the side that seems more tough. This right side is a lot longer, so it's tougher. It's easier to simplify. That's why we picked the tougher side, because it's easier to simplify than it is to make bigger. So let's just rewrite what we're working with. The 1 cosecant theta, we don't need the 1, just get rid of it. So cosecant theta, cosine theta plus sine theta. Alright, so we need to get cosecant theta, cosine theta plus sine theta to equal cotangent theta plus 1. So somehow we need to make it that. We need to get cosecant and cosine and sine to be cotangent. We know cotangent is cosine over sine. So that's a start. We have cosine, we have sine, but what about this nasty cosecant? Cosecant has nothing to do with cotangent. But we can make cosecant something. So it matches everything. We want everything to match as best as possible. Since we're already working with cosine and sine, let's see if we can switch cosecant to cosine or sine. And we can, because cosecant theta is the same thing as 1 over sine theta. So we're going to switch this to 1 over sine theta. Alright, we did that for multiple reasons. We did that because cotangent, the gap, the bridge between cotangent is cosine and sine. And we're working with cosine and sine. So that's why we switched it. Now that everything is matching and nice and neat, what do we usually do when we see parentheses? We distribute. So we'll distribute. We'll have cosine theta over sine theta plus sine theta over sine theta. Now let's simplify. So cosine over sine, that's just cotangent. So cosine theta over sine theta is just cotangent theta. So let's switch this to cotangent theta. And then sine over sine, that's just 1, because that's the same thing over same thing. That's just 1. So plus 1. It's the same thing. We made it equal. That's it. We're done verifying. All of this is your answer. So there's nothing to box. I'm just looking for the work. This part right here, you don't need to show. You don't need to show me what you're doing. This is just for the notes. But I need to see all of this. It's really tough, unless you've taken trig before. It's really tough to go from here to here. Don't go from there to there. I need to see all the work. I need to see this, this, and this. I need to see all the steps here. If you're worried about not showing enough work, show it all. Alright, so we have to verify. We have tangent squared x times 1 plus cotangent squared x equals 1 over 1 minus sine squared x. So which is the harder side? Now you might be saying fraction is harder, but remember, that's not the case. Fractions doesn't always mean the hardest. The harder side is the left side. Why? Because it's longer. There's parentheses, there's distributing, there's squares. There's just a bunch of stuff going on. So let's work with the left side. Now, is it possible to work with the right side and get to the left side? Absolutely. You can work with the right side. It's just going to be a lot more difficult. So we're not going to do that. We're going to work with the left side. Okay. So we need it to equal 1 over 1 minus sine squared x. Right now, we don't have sine or cosine anywhere, so let's not switch anything, because nothing is cosine and sine at all. It's just tangent and cotangent. So what we're going to do is what we usually do when we see parentheses, we usually distribute. So let's go ahead and distribute. So we have tangent squared x times 1, so that's tangent squared x. And then we have tangent squared x times cotangent squared x, so that's just cotangent squared x times tangent squared x. Let's see what we have. So we have tangent squared x. That's just tangent squared x. Okay, good for that. But what about cotangent squared x and tangent squared x? Do you see anything there? They're reciprocals of each other. Since they're reciprocals of each other, because that's an identity. Tangent and cotangent are opposites of each other. Since they're reciprocals of each other, it equals 1. So we have tangent squared x plus 1. Okay, we're getting there. You see how I can't tell you what to do? It's just knowing your identities. All of them, through and through. It's practicing your identities. Alright, so we need to get 1 over 1 minus sine squared x out of this. So we need to somehow get sine out of this. Somehow. So let's see if there's anything that we can do to tangent squared x. So tangent squared, I can switch it to cotangent, but that's not going to do me any good, right? Let's look at our identities. So looking at all of our identities, we have tangent squared plus 1. That's what we have. That's what we have left over. Do you see anywhere in here that says tangent squared plus 1 equals something? Right here. Tangent squared plus 1 equals secant squared theta. So yes, you are going to have to know things like that. You're going to have to be able to come up with those identities kind of out of thin air. But they're not out of thin air. It's recognizing them when you see it. So we know tangent squared x plus 1 is the same thing as secant squared x. So we're going to switch this to secant squared x. Remember, don't forget your goal. Our goal is to get this to equal 1 over 1 minus sine squared x. So remember, that's our goal. So we have secant squared x. Now let's see if there's anything that we can do. So we needed 1 over. We need a fraction. We don't have a fraction yet, so let's make a fraction. To make a fraction, we know secant squared x is the same thing as 1 over cosine squared x. So let's switch this to 1 over cosine squared x. Now I need 1 over, so we have the 1 over part, great, but we need 1 minus sine squared x. So we have cosine squared x. Anytime you have a function that is squared, go back to your identities. Do you see if it equals anything? That we have cosine squared x. We have cosine squared x. If we move that around, could we get it to be 1 minus sine squared x? We could. So we're going to use our Pythagorean identity. So using our Pythagorean identity, we know that cosine squared x equals 1 minus sine squared x. The Pythagorean identity we're using is cosine squared x plus sine squared x equals 1. So we subtract it over. And that's how we get the 1 minus sine squared x. So we switch this to 1 over 1 minus sine squared x. And that's it. We're good. That's all we needed. It equals. They're the same now. They're the same. So we're good. The whole left side, that's your answer. Alright, example 3. So we have tan t minus cotangent t over sine t, cosine t, and we have it equaling secant squared t minus cosecant squared t. So the left side is the much harder side. This is where the fraction is harder. So we have tan t minus cotangent t over sine t cosine t. Alright, so we need to somehow make this two equations that are being subtracted together. We only have one right now. We need it to be 2. So what we're going to do is just split it up. How we split it up, it's using that like little formula, a minus b over c is the same thing as a over c minus b over c. So we're going to split this up. So we have tangent t over sine t cosine t minus cotangent t over sine t cosine t. So we split it up into 2 because that's where they originally came from. You would usually go here to here, but we're just going backwards now. Okay, so we're getting there. Now we have 2 equations. We are getting there slowly, very slowly. Okay, I want to, because we need to get rid of the fractions, because we're not allowed to have that fractions because it's secant squared t minus cosecant squared t. So we need to get rid of the fractions, and to do that we need to get rid of the numerators. So how we do that, remember a over b, it actually came from a times 1 over b. So we're going to move it to the side. So we'll have tangent t times 1 over sine t cosine t. And that's minus then our cotangent t times 1 over sine t cosine t. You see how we're just doing all algebraic steps backwards? So, right, we would usually distribute and then we would combine. We're just going backwards. We're getting there. We need to get rid of all of these tangent and cotangents. We need to be secant and cosecant only. So to do that, I want to get rid of tangent and cotangent. So we know tangent t is the same thing as sine t over cosine t. And we know that cotangent t is the same thing as cosine t over sine t. So let's replace those. So tangent t, we have sine over cosine. And then for cotangent, we have cosine over sine. Alright, so we're switching everything. It's starting to match now. Now let's see if we can do anything. So we have sine t over cosine times 1 over sine cosine. Then we have cosine sine times 1 over sine cosine. I don't know if you see it, but left and right we can cancel out some functions. We can cancel out sine, and we can cancel out cosine and cosine. So what we're left with, all together, we have 1 over cosine cosine. So we have 1 over cosine squared t minus 1 over sine squared t, because we have two sines. Now, don't forget, what's our goal? Always check back to see what your goal is. Our goal is to get secant squared t minus cosecant squared t. We are so close, because what do we know about 1 over cosine? 1 over cosine squared t is the same thing as, you guessed it, 1 over secant squared t. And then 1 over sine squared t is the same thing as 1 over cosecant squared t. So we're going to switch them. So we can switch it using the reciprocal identity. So 1 over cosine squared t is the same thing as secant squared t. Then we have minus 1 over sine squared t using the reciprocal identity. Just comes out to, just cosecant. Cosecant squared t. Now that is our goal. We're done. It matches. Your work is all of it. That's your answer. All of it, this is your answer. Alright, let's verify. We have cosine x over 1 minus sine x equals 1 plus sine x over cosine x. So both of these look pretty similar, both sides. There is a harder side though, the right side. How do I know that? Because there's a binomial on top, but it doesn't matter. You could work with the left side and you'll still get the same answer. Well, it'll still verify. It'll still verify. So we have 1 plus sine x over cosine x. So where the heck do we go from here? Nothing is squared. Nothing is squared, so we can't switch it with identities. It has to be squared to be a Pythagorean identity. But what we can do is make it squared. That's this hint right here. Hint number 6. That's what we're going to do. Anytime you see 1 plus sine x, 1 plus cosine x, 1 minus cosine x, 1 minus sine x, anytime you see that, you're going to multiply by its conjugate, top and bottom. Why can we do that? Because if you multiply top and bottom, you're multiplying by 1 and it doesn't change the value. So we're going to multiply by the conjugate, top and bottom. Now, we're allowed to do that because technically we're multiplying by 1. When we multiply by 1, it doesn't change anything. So we're good to do that. We are allowed to do that. So we're going to multiply by 1 in the form of 1 minus sine x. You usually do this when you have 1 plus or minus sine x and 1 plus or minus cosine x. So you always multiply by the conjugate of what you're given. Alright, so on top, since it's a difference of squares, they're same but different. The only thing different is the sign. We just square everything, so 1 minus sine squared x. And on the bottom, we leave it factored out. The bottom you want to leave factored out unless you have to multiply it, but leave it factored out. So on top, I don't know if you see it, but anytime you see a squared sine or cosine or tangent or secant, look for your identities. So 1 minus sine x squared, sine squared x, that's cosine squared x. That's the Pythagorean identity. So let's switch that. So we'll have cosine squared x over cosine x times 1 minus sine x. Now let's see if we can get rid of anything. So remember, cosine squared x, that's technically cosine x times cosine x. Now we can cancel out the cosines, just one of them. So what we're left with is cosine x over 1 minus sine x. That's all we needed. We got it. Cosine x over 1 minus sine x. Cool. The biggest thing you can do is always know your identities. Study your identities, study equivalent forms of identities, so add and subtract some things. Then this will become a much easier section. It's literally just knowing and seeing your identities. This is going to take a lot of practice, You need to hone in on Chapter 5. Chapter 5 has to be your strongest chapter. Alright, let's work with both sides. When do we work with both sides? So, if both sides of the identity appear to be equally complex, the identity can be verified by working independently on each side until they are changed into a common third result. So meaning, we take the two sides and we find something they both have in common. So they're completely different, but let's find what they have in common. So, when to work with both sides? Well, when it looks crazy like this, when both sides are just insane looking. But that's okay, we can still do it. So let's just work with both sides separately. So let's work with the left side. Alright, so our left side we have secant A plus tangent A over secant A minus tangent A. Where do we begin? That's the great question. What's our first step? So where to start, it's just a good idea where to start. Sometimes it works, sometimes it doesn't. The denominator that is simple is cosine squared A. So let's try to get both to have cosine squared A. So to get that, there's no cosine anywhere in my first one. So I'm going to make it have a cosine. So we're going to multiply by the form of cosine over cosine. So to do that, we're going to multiply by cosine A over cosine A, which remember is just 1. So we're going to do that. Multiply cosine A over cosine A. Remember that we don't actually multiply, we just put it together. So we'll have secant A times cosine A plus tangent A times cosine A. And that's over secant A times cosine A plus minus tangent A times cosine A. Alright, so we did that just to try and make it the same on the right side. That's all. We're just trying. Let's see if it works. Now we have secant times cosine plus tangent times cosine over secant times cosine minus tangent times cosine. Do you see what we have here? We have reciprocals. Since they're reciprocals, they equal 1 when you multiply them. So we have 1 and 1. So now we have 1 plus tangent A times cosine A, and then 1 minus tangent A times cosine A. So our first step, the Barney pink step, that was just to try and get it to match using cosine. Since the right easy side, the easier denominator is cosine, that's why I multiplied by cosine. From there, we're just simplifying now. From here, we're just simplifying from what we know about functions. Alright, so we have 1 plus and 1 minus tangent times cosine. We can switch tangent because we know tangent A is the same thing as sine A over cosine A. So let's switch our tangents. So we have 1. So we switch our tangent to sine A over cosine A. And that still times our cosine A. Alright, we can cancel out our cosines. So what we're left with now is 1 plus sine A over 1 minus sine A. You see how that's pretty simplified? Nothing is squared. There's no complex fractions. There's really not much more we can do. We'd have to multiply by stuff. We'd have to make it. So let's see what we can do from now for the right side. So we're done with the left side. Let's see if we can get the right side to equal this. How do you know if you're done? When you can't simplify anymore. I cannot switch sine A. I cannot switch sine A because they're attached to the 1. So I can't make it like, why would I do 1 plus the reciprocal, right? It doesn't make sense to do that. So we leave it here and see what we can do to the right side. So the right side. So now that we have something simplified on the left, let's see if we can get our right side to equal 1 plus sine A over 1 minus sine A. Let's see if we can do that. So our right side, we have 1 plus 2 sine s plus sine squared. Oh, that's supposed to be an A. That's supposed to be an A. Over cosine squared A. Alright, so we have 1 plus 2 sine A plus sine squared A. Now we have a polynomial on top. We have a trinomial on top. We have a trinomial, so we have to factor it. So we can factor. We could factor this down into 1 plus sine A squared. That's like if we had x squared plus 2x plus 1. We factor that into x plus 1 squared. Same concept. If you took me for college algebra or intermediate algebra, you know what I'm talking about. I actually bring this up in those classes just to show you this is the future. Here we are. So we're going to switch that to its factored form. So its factored form is 1 plus sine A squared. And that's still over our cosine squared A. So cosine squared A. So our goal at the very end is to have 1 plus sine A over 1 minus sine A. So let's see if we can do anything. Anytime we see a function by itself and it's squared, you're usually going to switch it. So yeah, we're going to switch this because it's a Pythagorean identity. So the Pythagorean identity is cosine A plus sine squared A equals 1. So if I need it to be cosine equals, it would be cosine squared A equals 1 minus sine squared A. So we're going to switch that. So on top, we have 1 plus sine A squared, and on the bottom, we have 1 minus sine squared A. So we can factor 1 minus sine squared A. How can we factor that? Well, it's a difference of squares, because we have a perfect square, a minus, and a perfect square. So remember, a difference of squares, if we have a squared minus b squared, it's the same thing as a plus b, a minus b. So we take the square root. So on top, we haven't touched it, we still have 1 plus sine a squared over, so we factor the bottom into, so the square root of each of them. So the square root of 1 is 1, and then the square root of sine squared a is just sine a. So you're going to have a plus and a minus version. Now we have 1 plus sine a's on the top, and then we have 1 on the bottom. So we can cancel out one of them. So what we're left with is 1 plus sine a over 1 minus sine a. That's it. We got them. They're both the same now. So how we would write our answer, because literally all of it is our answer, but there is a right way to write this because we found equivalence. We found something they're both equal to. So how we would say this So that's how we would write our answer, just letting the reader know we got to our answer because we were able to simplify both sides to an equivalent form. Example 6, we have cosecant x over cosine x equals cotangent x plus tangent x. Now, you could work with one side, you could work with both sides. I'm going to work with both sides because cosecant and cosine, cotangent and tangent, we have a bunch of reciprocals going on here. So I'm going to work with both sides separately. So I'm just going to simplify both sides and see what happens. So we have cosecant x over cosine x. So cosecant. Like, let's get rid of that reciprocal right now. We know cosecant, we can switch that. Cosecant x is the same thing as 1 over sine x. So let's switch that. Now let's see what to do now. If we switched cosine to its reciprocal, if we switched it to secant, does that do us any good? No, because we don't want the reciprocals. We want like the normal, we want sine, cosine, tangent. That's what we want. So let's keep change flip this, because that's what it's telling us to do, it's telling us to divide these. So let's keep change flip. So we have 1 over sine x divided by cosine x, so that's 1 over sine x times 1 over cosine x. So what we're left with is 1 over sine x cosine x. Now there's nothing more I can do because they're not squared. They're not squared, and they're also not plus or minus anything. So let's see if we can get the right side to simplify down to this. When you think you can't do anymore, start the other side. Because nothing is squared, why take the reciprocals? Let's see if we can do anything to the right side. Okay, so for the right side, what can we do here? Well, we have 1 over sine cosine, so I want to make these sine and cosine because that's what the left side is simplified down to, sine and cosine. So let's do that. So we know cotangent is cosine over sine. And then tangent, we know that is sine over cosine. So that's that tip of when you don't know what to do, switch to cosine and sine. Usually works. Here we go. So it's telling us to add these, so we have to get the common denominator, so times sine x times sine x times cosine x times cosine x. So on the top we have cosine squared x over cosine x sine x plus sine squared x over cosine x sine x. Now that they have the same denominator, we can go ahead and just make it one fraction. So we have cosine squared x plus sine squared x over cosine x sine x. Alright, we have functions that are squared and a plus sign, so we know that we should be looking at our identities. So we know cosine squared x plus sine squared x equals 1. So we're going to switch that to 1 using our Pythagorean identity. So we have cosine squared x plus sine squared x equals 1, and that's over cosine x sine x. That's it. We're good to go. They're the same thing. Remember, for multiplication, it doesn't matter the order. So since they both equal the same, they have common ground, we're done. So how we would write our answer, we have cosecant x over cosine x equals 1 over cosine x sine x, and that equals cotangent x plus tan x. Example 7. Applying a Pythagorean identity. Tuners and radios select a radio station by adjusting the frequency. A tuner may contain an inductor L and a capacitor C. The energy stored in the indicator at time t is given by L of t equals k sine squared 2 pi ft. And the energy stored in the capacitor is given by C of t equals k cosine squared 2 pi ft, where f is the frequency of the radio station and k is a constant. The total energy E is in the circuit given by E of t equals Lt plus Ct. Show E as a constant function. Okay, so it tells us we have Et equals Lt plus Ct. So we want to show that it's constant. What does that mean? We want to show it equals k. So what does that mean? Show that e is constant. We want to show that e of t equals k. That's what that means. As remember, constant always means k in math. 6.8 college algebra. So it gives us a formula about et. It tells us that e of t equals L of t plus C of t. We have L of t and C of t. It gave us those. It gave us LT. So let's plug it in. So LT is k sine squared 2 pi ft. Then we're going to add that to CT. And CT is represented by k cosine squared 2 pi ft. Alright, so we just plugged it in because that's the equation they want us to work with. They want us to work with LT plus CT and make it simplify down to just k. So they both have something in common. They both have a k. So let's take it out because that's what we actually ultimately wanted to get to. So let's take it out. So we have e of t equals the GCF, which is k. So now we have sine squared 2 pi ft plus cosine squared 2 pi ft. You might see it. We have a Pythagorean identity. So they both have the same 2 pi ft. That's the actual theta. So theta in this example is 2 pi ft. Remember, theta is always with the variables. You can have multiple variables. So we have basically sine squared theta plus cosine squared theta equals 1. So let's switch that. So we have e of t equals k times 1, which when we simplify, what's k times 1? Just k. So e of t equals k. So because k is a constant, e of t is a constant function. So we proved it is a constant function.